forgot to press record. So, Will was the only one absent today, right?
It'll be fine.
Okay. Will, if you're watching this video, check out the guided notes for the first page, okay? Alright. We are gonna check. Did you guys get negative 0.3333? 3333, and then 0.5? Alright, if you are making calculator mistakes, let's figure out why, okay? Alright, so this is what I should have put at the very beginning because of us trying to prove, or that example 2 that asked you guys to decide which one was allowed. It's so silly that we didn't ask this first. So this is that property, the definition of a log that I gave you. So here's your definition of a log, more written out for you, nice and pretty. And it's b to the y is equal to x. And these are equivalent. So this is called log form, and this is called exponential form. Now, we use these interchangeably. If I need to solve a log, I convert it to an exponent. If I need to solve an exponent, I convert it to a log. So if my unknown is up in the exponent, I consider it stuck, okay? My x and my unknown value I'm trying to find. If it's stuck up in the exponent, by converting it to a log, notice how y is no longer stuck. Now, if I have a log and my variable I'm trying to solve for is stuck in the log, notice how when I convert it to an exponent, it's now unstuck. It's now solved for. So that's why these equivalent properties are used, and we use them interchangeably to solve. And you're going to be solving logs and exponents this way. Okay? All right. Let's go ahead and move to your next page and start going through some of these examples. So first off, I want you guys to be able to write things in the equivalent form, and it looks like you guys are allowed to like simplify it out if it is, okay? How would you guys write this one in its equivalent form? Give me its equivalent exponent.
5 equals that.
Close. So the base of your log, very good. The base of your log should be the base of your exponent. So they're inverses of each other, so those bases should match, okay? So my base of my log, and that's a common mistake when you guys are running on autopilot. I see people who mix up where the 2 and the 5 goes, okay? This simplifies to 25, not 10, correct? So make sure you guys are not timesing those, that it is an actual exponent. So, all right, let's convert b. This one isn't a solving one, it's just converting, but let's convert it. And if you guys want to check, put that in your calculator. Is log of 25 over log of 5 2? Like check if it's equivalent. But when we do the converting, it proves it too. So someone hurry and convert this for me. Well, convert like the process. So 5 squared. Yep, I call this around the world. You do your around the world conversion. And it is true, right? And then if you guys try this in your calculator, it also gives you a 2. All right, will you guys convert this one? What happens when we try to log a 1? Let's see what happens. Do the conversion for me. We're not solving anything, so do the conversion for me. Like write out the conversion. The base is 7 to the 0 is 1. So notice if I try to log a 1, it always gives me a 0, and here's why. No matter what the base is, if I raise it to a 0, it's a 1. So anytime you guys log a 1, it'll be a 0 in the end. Okay? So the conversion just validates kind of the answers that you guys get when you try stuff in your calculator. All right, 25 will be raised to what? 1/2, and that'll be equal to, is this a true statement? What's 1/2 technically? It's a what? It's a 1/2 is technically a square root, isn't it? So is the square root of 25 5? Yes. Okay. Let's go the opposite direction. This way is easier because I think it's easier to do this little around the world thing. Like I think it's easier to start with the base and do that. Exponents backwards are the harder direction because it's a little trickier. So I always start by writing a log, and I always start next by writing what the base is. If the base of my exponent is a 6, then the base of my log has to be a 6, okay? And then whatever is stuck up in the exponent is the part that's by itself when it's in a log. So what goes right here on the right side? Or I could have put the equation on the left, it doesn't matter, but what's by itself? 0, and what's inside the log? Good. Logs never stand alone, they're a function. And so you guys, whenever you guys are working with logs, you can't just be like, divide by log. I'm like, log of what? Because logs have to have a number connected to them. okay? So this is log of 1 with a base 6 is equal to a 0. So once I put it into its log form, I will do my little around the world check to make sure I have the proper exponential, okay? All right, let's write this as a log. How would you guys convert this one? Log base 4 of 16 should equal x. Good job. Check your around the world. 4 to the x is 16. Good. Log base 1/3 of -4 is 81. One more. This one looks a little bit crazy. What must you?
It can't be negative though. So
That's true. This would turn into an empty set. But where we are just converting, I was just going to have you convert. But if we aren't really solving in this case, so where I was just having you guys convert, that's fine. You can just do that. But yes, you're correct, Daniel. All right, what do I do on this one? Because it's not an exponent, and we think it's not an exponent. But what are radicals technically? Rational exponents. So let's write that rational exponent. It's actually 32 raised to what? 1/5. Now I can convert it to my log. So let's go ahead and do my log base 32 of 2 is equal to 1/5. And then just check your conversion. Do we feel pretty good on those conversions? Can we go back and forth from logs to exponents to logs? Okay. That definition of log is what you guys are going to kind of live and die by when you guys are solving and simplifying logs, okay? So make sure you guys know this properly. Okay. All right, let's do, the value of logarithms can also be found by using the law of logarithms. So not only are you forced to do the conversion, every once in a while, you guys might be memorizing some of these laws or using conversions to kind of prove those laws, okay? So the following major properties of logarithms can be developed from corresponding properties. So the properties are used in solving exponential logarithmic equations. They work for positive values of x and y. So we got to assume x and y is positive in these cases. Does that sound good? So try to just assume that on all of these x's and y's. All right, the following properties of logarithms follows our conversion right here. And remember, the conversion, like we said, works both ways. So let's go through some of these properties. Any base, and these are rules I kind of want you to memorize. The more you can kind of memorize, the more efficient you can be, okay? So when you guys look at these, anytime you try to log a 1, I don't care what the base is, it's always going to be a 0. Always, always, always. And we already did this one just a second ago. And that's because a to the 0 will always be a 1. So that's property number 1. Another property. What do you guys think happens when I log an a and the base was an a? Well, it's a 1. And let's see why. Why? If I were to log a 2 with a base 2, why is it a 1? Well, let's convert it. Let's use exponents to see. A, when raised to 1, is just a. Duh, right? So that's why when you're logging something and the bases match, the number inside that log matches its base, then you guys know that it's just a 1 when you're done. Oh, this didn't convert very well. That n should be up in your exponent. Did your guys' PDF print properly? Yeah. Okay. If I log a base a and my exponent is an a to the n, the result will be n. And this, I want to tell you two things. A raised to n would have been equal to a to the n. But I want you guys to, I don't really love the way they converted that. That's an obvious property there. But whenever you guys do inverse properties, if I have a and the log is an exponent, because they are inverses of each other, they undo each other. And this works also this way. If I have a log base a and then a to the n, this log undoes that exponent. It undoes it. And so it's like me square rooting an x squared. Like they're inverse properties. So it's like I'm logging an exponent, and so that exponent is cleared essentially, and I am left with my n. So this is known as your inverse property because logs and exponents are inverses. And so if the basis of the log matches the base of the exponent, you gotta just take the exponent. Okay, so it's like it undoes it. Okay, kind of a tricky property, but that's called your inverse property. All right, there's also one-to-one properties. If I am logging both sides, shouldn't it be that whatever is inside is just equal? So it's almost like I can just clear those logs. Now, if we were to take the time to convert and solve, the logs would go away anyway. But this is just a one-to-one property saying, hey, log of x equal to log of y just means x has to be equal to y. So you can just assume that your logs are going away. Okay, and these properties are the same ones we used last year. You learned most of these in Math 3. So hopefully some of them are coming back to you. All right, using these 4 properties, hopefully you guys could solve logarithms just fine. So what is log base 5 of 5 going to be? What is x going to be? What did we learn?
It's going to be 1.
The exponents undo each other, and so your x ends up being a 1. When in doubt, convert it to an exponent. So if you're stuck and you can't think of what the x is going to be, then convert it. 5 raised to what would have given me a 5 to the 1. And here's another one-to-one property. If your bases match, don't you guys think that you should be able to say that x equals y? If your bases match. So that's another property you could kind of add to your one-to-one-ness, I guess, is, hey, if I convert this and my bases match, I can just assume that x is 1. Okay? So when in doubt, I like to convert things to their exponent. Okay? Here is another, our rule. What rule is this one? Rule what? Look up at your guys' earlier rules. What do you guys notice? Your rule 3? What do we do on rule 3? If I have an exponent raised to a log and that log is a base 5 and they match, they undo each other. So what will this result in? X will be 7. Yep, they undo each other. When in doubt though, you guys can convert this back to a log. So currently this is technically almost like an exponent. So you guys could sit there and say, hey, I have a log base, well, I can convert that. It's actually really tricky to convert. How would we convert that one? So I would have, whatever was stuck up in the exponent is now by itself, right? Log base 5 of 7. Whatever was stuck up in the exponent, so this would have been, oh my gosh, my brain's not wrapping around this. 5 to the x then, right? So whatever was stuck up in the exponent is now 3. And that 5 was raised, that is equal to 7. Yeah, that one's a trip to convert. That one you almost just have to memorize your inverse properties and realize that those are inverse properties of each other, so you can just solve it and say that it's 7. That one's a really tricky one to go backwards and simplify. Okay, what about this one? What is x here?
0.
Good. Why?
Because it's a log of a 1.
Yep, it's a log of a 1, and 7 to what gives me a 1, right? Think of it that way. The only thing x could be is it could be 0. All right? So those converting, those ones are, how many of you kind of briefly remember some of those properties from last year? Awesome. Some of us don't, and that's okay. And I think with your homework, giving you guys a few more examples, these guided notes to refer back to, I'm hoping you get nice and practiced up with that, okay? All right, and this is where I feel like there's some things that are you guys are kind of like our little guinea pigs, and we're going to be talking about LNs, which we didn't really talk about those yet, but remember how I said ln is the same thing as a log base e. So if you guys ever see an ln, you treat it like it's a log base e, okay? All right, let's go ahead and solve. What would be your guys' methods to maybe solve for this one? What would you guys do? change of base could work, but what if I said, oh, you can't use your calculator? What would you do next?
Exponent.
You turn to an exponent. So I would say, well, 4 to the x is equal to 256. And so this introduces another strategy. Another strategy is to manipulate and create that one-to-one principle that I just told you on the other page. You guys can refer to your other page if you want. And you can realize, hey, if I rewrite my bases to match each other and manipulate it, then I know that that x will equal my y. So my strategy would be to kind of break the 256 down to 4 raised to anything. And if I can't raise it to 4 to something, can I raise it to 2 to something? Okay? So let's manipulate. So you would have to use a calculator for this technically, but let's go ahead. We don't want you guys to just plug in and change base on these ones. We want you to learn the manipulation skill. We want you guys to learn how to be able to manipulate things to look the way you want them to. Okay? So let's just play dumb that we don't know the change of base, because you can't do change of base here, and you can't do change of base here or here. So even though you can technically do the change of base here, let's still do the manipulating steps. Cool? Can anybody think how to break 256 down? Would somebody break it down and tell me, is it an exponent of 4? 4 to something? It is. Okay, good, Karsh. What did you get?
4.
You got 256 to be a 4 to the 4. So we get to say x is what? 4. Easy enough. Now this one's trickier. Now we don't know the base. And it's impossible to get into that. So next, we would do our converting. Okay, x to the what? X to the second is 16. Do I know how to solve something like this? I do. What do? Yep, we would square root. Now what do we have to assume x's and y's are on these? Positive. So even though you normally say plus and minus, will you guys just take the plus when we're working with bases? We can't have a negative base. And, so just do a plus 4 on that. Okay? Alright, let's try this one. ln of k is -1. ln is a log with a base e. It's the inverse of the exponential base e. It's a log that matches that base, I guess. So they get to undo each other. So whenever I want to write this as a log base e, I can visualize that there's an e there, or I can actually write it if you really want to. Let's convert this now. It's going to be e to the what? E to the -1 is k. So therefore k is 1 over e. Did it say on top that we need to round it to a decimal? Because I'm okay that we leave it. I'm okay we just leave this. 1 over e. Do not do decimal. We don't say round it, just do 1 over e. Okay, how would we solve g? This one's going to take some manipulating, so I want to do this one together. X to the
-4.
x to the -4 is 1 over 625. There's a couple approaches to this, but I think you guys can. I wonder if there would be the best approach in this one. You can manipulate using exponents. You can try to rewrite. Gosh, I don't love the idea of 4/3, but we may have to just do that. So mathematically, what do we know we do with negative exponents? What would be the way you guys would try to simplify this? What would I do with that? Flip it. So I can make this a 1 over x to the 4. But now both sides are in the denominator. Are we allowed to technically times those out and move them to the top, or flip both sides and it's still equivalent? As long as it's both sides, are we allowed to? Yeah, that's how proportions work. As long as whatever was on top and bottom, and if you were to do the cross product to solve, you guys can do that. So I can technically rewrite this as x to the 4th is equal to 625, and then we can technically 4th root both sides. Now with 4th rooting, you normally would have both a plus and a minus, but we're just going to take the plus, okay? Do you guys mind telling me what the 4th root of 625 is?
4.
5 times 5 times 5 times 5, right? So it's going to be 5. So your answer would have been x is equal to a positive 5. So it takes a little bit of manipulating, trying to get, you guys gotta know your exponent properties. We need to know our radical properties. We need to know all of that stuff that you guys have learned throughout. All right, let's do this one. A to the what? a to the third is equal to 125. So we could go to cube root both sides. I could also, if you guys are pretty good at your number sense, I might look at this and say, well, I know this is 5 cubed. So if a cubed equals 5 cubed, hey, my a must be 5. But I could also cube root both sides. I would have just got 5. Okay? Alright, here is one that has an ugly pi. But if you guys know properties, it looks scary and daunting, but it's, if you guys just kind of slow down and break it down and try to remember these properties, it's not as daunting as it looks. Now, I normally, when I see a log, go to convert. But does anybody notice something before we waste time doing that?
They cancel each other.
Yeah, a log with a base pi, and then my exponent's a base pi, they undo each other. So they're canceled functions. They're inverse functions of each other. So that essentially just ends up being a 12. So when you guys notice the similarity in your log's base and your exponent base, just know that something's going to simplify nicely for you. Okay. All right. Logs last year, we didn't kind of do them as in depth as this, so I'm hoping that there's enough knowledge from last year, and now that we're making this a little bit trickier, I'm hoping that's coming together okay. Just let me know if you guys get some on your homework that you don't understand. All right, we have just a couple more examples, and oh, we actually do. I forgot. We do graph logs. Luckily, it's just the basics of logs, so I think we have to do the transformations. Let me think of these, and I want to jump around and try to skip some. Okay, we were just solving ones that you convert. Some of these have logs on both sides, some of them don't. Let's for sure do A. Okay, what would you guys notice on A?
X would equal 7.
There's logs on both sides, so do I even need to worry about those, or do I just technically get to take the inside? You gotta take the inside, right? What do you guys notice will happen on this one?
It's a 1.
It's a 1. Very good. What do you guys notice x must be here? A 1, right? Because 3 to what would give me x, and it's a 1. Good. Now these ones take actual solving. These ones have multiple, like a binomial inside, and so it's just going to take you guys doing your normal solving skills. Okay? Let's go ahead and set this up though. I love converting logs to exponents because it puts it in a form that we're all familiar with, right? So it's an easy conversion. So once you know the conversion, these are super easy to solve. At first glance, you're like, oh no, it's a log. But then when you realize, oh, it just converts to an exponent, it's super simple. So this converts to a 2 what?
Squared.
2 squared, and then it's equal to 5x plus 3. We know how to solve that. So we would just go ahead and minus the 3 and divide by 5, okay? Minus the 3 and divide by 5, you guys can check that. And you guys should be getting in. What did you guys get when you minus a 5 or 3 and divide by 5? You should have got 1/5. Check your work and see if you guys get 1/5 on that. I'll pause for a second and see if you can get caught up. Alright, whenever I see LNs, I'm like, oh dang it, it's gonna be not nice whole numbers because they're, you know, it's gonna be using an E, and E is this decimal that doesn't end. It's like 2.7 whatever, and it doesn't ever end, okay? So we're gonna go ahead and convert it. So how would you guys convert this LN?
E4.
E to the 4, yeah? 2x minus 1. Now, I need you guys to put that into your calculator because it's a decimal, and then please don't round. I want you guys to get in a habit of leaving stuff in your calculator as long as possible, and then you round at the very end if you don't mind, okay? So let's go ahead and try it together. Everybody hurry and put e to the 4th in your calculator, and then leave it. Don't write that decimal down. I'm going to write it down so that we can see that you guys are close, but I'm going to ask that you use your calculator, okay? The more decimals you go out in your notes, the more accurate you're going to make your final answer. So try to go as many decimals as you can if you do round. Okay, what would I do to what's in my calculator next? Add a 1. So leave what's in your calculator and add a 1 to it. And then what are you going to do? Then you're going to take whatever that value is, and you're going to also divide by 2 and divide by 2. So when you guys actually get your answer, let's check that what we got is the same. Are you guys getting a 27.7991 in your calculator? Okay, good. Check into that if you aren't, and maybe you did the E part wrong. A lot of people, if you had not pressed equal, A lot of people also forget to close the parenthesis on the e. So if you guys knew you were going to take e to the fourth, add a 1, divide by 2, and you didn't press equal ever, you maybe forgot to close a parenthesis. So just be careful of that. I like to press equals as often as I can because I'm lazy with closing my parentheses, so I just try to press equal when I can. All right, what would I do here? 2 to the 5th is 8x plus 5. Okay, I think you guys are getting it. 32 is equal to 8x plus 5, and we end up minusing a 5, minusing a 5. So 27 is 8. That gives me a decimal. I'm just going to leave it as 27 over 8, but if we ask for decimals, you guys just get a decimal. All right, so finding, back when we, well, let's look at this one actually. ln and e is like me having a log base 2 of a 2, okay? If I had a log base 2 of a 2, then I would have known that this would have just cleared, correct? Well, that's how ln of an e works. Ln and e, they're inverses of each other. So this technically is what? Negative 4x equal to 8. Because when I ln and e, they're gone. And they undo. Okay? Alright, we end up with a negative 2. Okay. Now, back on lesson 35, we found inverses. And I want to show you kind of almost like a proof as to why converting it to an exponent works, why they're equivalent, and I want to show you what this inverse is going to look like, okay? So back on lesson 35, we found inverses by swapping what? What did we do when we found inverses? Swap the x and y's. So if I go ahead and I swap my x and my y, and then I want to solve for y, because that's typically what we solve for, we would do the conversion by doing 5 to the x is y. So notice how a log base 5 and an exponent base 5, how they turn in, they are inverses of each other. And that's why we are allowed to turn those into exponents. And so I wanted you guys to realize, like, what do you guys think this one's going to look like as a log? Just a log base what? 4 of x. Because that's how inverses work. So we're going to go ahead and do a 4 to the y is equal to x. And then we are going to convert it to a log. Log base 4. What gets to be freed? The y does. So log base 4 of x is its inverse. Okay. So you guys are pretty well versed in your finding your inverses, and so now we kind of understand why they connect us a little bit. All right, I forgot we briefly heard you talk about these logs because I know that we aren't making you guys do like crazy, like in your guys' 1050 courses, we will make you guys do crazy transformations. And transformations are heavily covered, and so I think you're gonna kind of just briefly graph a few of these, but luckily they're super basic. So everything with exponents and everything with logs are inverses. So if you guys think about how exponents work, whatever was an x on one turns into y's on the other. So on exponents, let's just recap all of your properties from exponents. And if you guys want to go back to that lesson 36 or 7, when did we graph exponents? 36? So let's go through those properties of exponents. They look like this. And let's just talk about how they had an asymptote at y equals 0. They have a domain of what? Covers everywhere. So what do we say when it's everywhere? All rails is our domain. And what was our range? The asymptote to infinity. And we had a couple values, like we had a value at 0, 1, and anyway, we had those properties that we set up if you guys watched that lesson with the sub, when you guys set up these graphs. So because exponents and logs are inverses of each other, everything about them is opposite. You just swap your x's and your y's. So for instance, like if this was a y equals to the x, then my y equals a log base 2 of x, everything would be swapped out that I had just found on a 2 to the x. In fact, you guys can graph that way. You guys are welcome to find its inverse and then just swap everything if that's easier for you, okay? So let's go through this really fast. We're going to assume our x's are all positive, and then we're going to do the inverse of a growth. So we're going to assume it's the inverse of like a growth b, like a base that's a b, or a growth of bigger than a 1, okay? Bigger than a 0. All right. If you guys think the domain on this exponent is all reals, what do you think is going to be, what's the all reals going to be when you go to its log? Range. If you guys notice this one's range was 0 to infinity, what do you think is going to happen with logs on the domain? 0 to infinity. In fact, I wish we would have hurried and just like stated these graphs really quick, because then it would have made more sense when you guys are finding domain at the first of the lesson. Here's my graphical representation, which we aren't doing shifts, so that would have been confusing. But then here's my algebraic computation. So what I just taught you on page 1, do you remember me saying, hey, inside my log has to stay above 0. Well, look, that's what your domain is. Does that make sense to everybody? So inside your log is above 0, and that's your domain. Now, look at the asymptote. If I have an asymptote at y equals 0, where do you think your asymptote is on a log? Switch the y's to x's. X equals 0. So the asymptote is a vertical asymptote. It's a vertical asymptote right here at x equals 0. And so it forms a boundary. So there's your boundary. Asymptotes are just boundaries. And I had a y-intercept at 0, 1. And so I can swap those, and I will always have a value at 1, 0. So if I had a y-intercept, I have an x-intercept. And then those are the basic key features of our parent function for logs. Okay, the next value you get, if I am trying to plug in values, I'm kind of strategic with what I plug in. So I usually always, on my graphs, I know that when I plug in a 1, I'll have a value of 0. And then if this was a 2 to the x, what would be a nice number to plug in next? A 2, because a log base 2 undoes a 2. Would plugging in a 3 be a nice number? No, right? So you can be strategic when you guys are getting your basic graphs by trying to be, what if this was a log base 3? Then I'd want to maybe plug in a 3 to get a 1. What if this was a log base 4? I'd plug in a 4 to get a 1. That makes sense to everybody. And when in doubt, go back to its parent and be like, oh, if I plug in a 1, there was a value at 2. So therefore 2, 1 when I do its inverse. So you guys can handle this a couple different ways, memorizing parent functions or going back to the parent of an exponent and then just flipping everything. Okay? I don't know what works best or how your brains want to handle these, but I'll let you guys kind of decide. Okay, let's do a couple of these graphs, do a couple of applied problems, and let you be on your way. Okay, I'm going to break down the characteristics. We have one that's a base 2, one that's a base 3, and one that's a base what? What is this one if I don't have a 10? Notice how I don't have any shifts because we're not doing transformations. Notice how we're not being too complicated. We just want to make sure you guys can kind of grasp the basic log, okay? On this day. All right, let's do it. Logs. What's my domain restriction? Again, I could think about its inverse if I really want to. What's the inverse of a log base 2?
2x.
Not 2x, but 2 to the x, right? What's the inverse of a log base 3? 3 to the x. And what's the inverse of a log base 10? 10 to the x. Good. Hopefully you guys are kind of starting to see that. What do we learn about the domains when there's no horizontal shift and it's just like the parent? There's that asymptote here, so my domain is 0 to infinity on all of these, right? So no domain shift on any of these. And again, if you don't want to view this as shifts, because we aren't working on transformations right now, you can do it as domain restrictions. Inside my log has to stay positive. Inside my log has to stay positive. Inside my log has to stay positive. You can do it algebraically. So not only do you kind of memorize that there's an asymptote there, but you can algebraically take what's inside your log and say, hey, this has to stay above 0, and then calculate it. Okay? So when you guys are asked domain restrictions, take what's inside, set it greater than 0, and solve. All right, what's the range on all of our logs?
Negative infinity.
All reals, negative infinity to infinity. Good. Do these ones have vertical or horizontal asymptotes? They all have vertical, right? Where is it?
X equals 0.
X equals 0. Oh, whoops. I wrote that up. I actually wrote that up. My bad. You guys can write it down by the asymptote. Where will these have x-intercepts? And when in doubt, you guys can also do what when you want to calculate x-intercepts? Instead of just memorizing, oh, all my intercepts, like, there's always a value at 0, 1, so I have a value at 1, 0. That's great. And there is one at 1, 0, but can I do anything else to find x-intercepts? Where would I plug in a 0 if I want to find an x-intercept on these? You can plug in a 0 to your what?
Y.
Your y and solve. So you guys could say, hey, log base 2 of x is 0. And then we already learned that property. Didn't we learn that when you log something and it's a 0, what had to have been the x? A 1. So this is also showing why your graph works out the way that it does. So all of these without any shifts will have an x-intercept at 1, 0. Because when I go to plug in a 0, log of 1 is a 0. Log of 1 is a 0. So you can actually take the time to calculate your x-intercept as well. Are there y-intercepts on this one? And while you guys are thinking about it, I'm going to start drawing what we've done so far. Okay, you say no. Why are you saying no?
So never touch the zeros on the line.
Yeah, I can't cross that vertical asymptote. It's actually undefined there. So when I can't cross something, it's a boundary. So there's no y-intercept. Now let's actually solve this algebraically though, okay? If I wanted to see if I could find a y-intercept, I could plug in a 0 to my x's. So I would get my g equals log base 2 of 0. Well, what did we learn happens when I try to log a 0? It's undefined. And again, we proved this because 2 to what would give me a 0? Nothing. 2 to nothing will ever give me a 0. So this will never happen. So there is not a y-intercept on any of these because that's where my asymptote is. Now, we're not doing shifts right now, but if my asymptote were to move to the left here, then yes, I could run into having a y-intercept. That's the only time, okay? But for these most basic graphs, you guys are never going to have a y-intercept if your asymptote is there, because I can't cross a vertical asymptote because that's where it's undefined. Okay. All right, and then it's increasing for our domain, right? This one is a growth, 0 to infinity. This one's increasing 0 to infinity, and this one is increasing for the interval 0 to infinity. So they're very, very, notice how there's not a lot of differences with these graphs. Now, I do want to get like another value just to make these a little bit more accurate. So let's go ahead and plug in at least one value. We said I would maybe plug in a 2, and when I plug in a 2 right here, what do I get?
1.
A 1. So I do have a value at 2, 1. Right? Oops, I didn't go through that very good. Okay, what's a nice value I should plug in here? 3. And when I plug in a 3, what's log base 3 of 3? 1. So it looks like I have a value over here at 3, 1. Are you guys seeing this pattern? Is anybody noticing our pattern on logs? As my base goes on, that gets a little bit flatter sooner though. Okay, what would I plug in on a log base 10?
10.
Possibly a 10, right? When I plug in a 10, what do you guys get?
1.
A 1. So that's out here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Ooh, I lost my count. I think it's that one. Yeah. So as my base does get bigger, are you guys noticing it turns like quite a bit sharper and stays like flatter vertically? Ooh, that was terrible. But they have a similar pattern. So hopefully you guys are noticing that pattern. I won't keep kind of running that by you. Let's do our last word problem and we'll get on our way. Okay? All right. The population of deer in thousands in a certain area is approximated by this logarithmic function. So we're able to approximate what's happening. Okay? And it makes sense because when you think about animals, you think about population. A lot of times you use exponents to kind of talk about the population growth because A lot of times with animals, they do grow exponentially. Some animals don't live as long, so there is some like discrepancies, but they can usually come up with a trend and a best fit. Your honors courses, you guys probably mess around in your calculators. Taylor and Torres really do a good job, I think, for those of you who are in honors, that if you're given like a set of values, you can put values into a graph, and where we can't use graph and calculators, we don't get to really do this in this class, but it's really nice to see a trend, and then you come up with the best fit line that shows you that's happening. And so they notice with like with populations that they can use exponents and logs to determine population trends, okay? The population of deer follows this, where X is the number of years since 2017. How many thousands of deer will be living in the area in 2024? What's this one asking us to do? This is a simple what? Is it a solving or is it a plugging in? This one's a plugging in one. So as long as you know what F represents and as long as you know what X represents, you guys will know where to plug something to. So this one's just a plug and chug, so you guys are going to go ahead and just do log base 5, and then I have my 100. What would I plug in for my X if they're wanting for the year? What'd you say?
7.
7. And then we would get this log base 5 of 700 minus 75. What do you guys get on that one?
625.
625. And then I could put this into my calculator as the change of base, but I also could see if 625 can be manipulated to be a base 5. Can 625 be manipulated? A little bit?
Yeah, it can be 4.
I could also convert, so there's like 3 approaches. You guys could do change of base. You guys could convert and say, hey, 5 to the y is equal to 625. Let's manipulate it. 5 to the y is equal to 5 to the what?
4.
4. Right? I could have also manipulated it here. I could have also said, hey, log base 5 and 625 is 5 to the 4, and that also tells me it's 4. So there's 3 approaches. If you guys use 3 different properties, you guys are able to solve this out. So we ended up getting 4, but that's for what? What did we just learn? 4,000. Thank you. Realizing that this is in thousands, we would say 4,000 deer in that year. Hopefully you guys can plug and chug. Now that we know how to solve, I do want to hurry and do one of these T questions, and I do apologize for taking more time out of your guys' seat work time, but if you don't have anywhere to go to flex, hopefully you guys can stay. Now that we know a little bit how to solve exponents using logs, we have a better game plan. I did show you guys one the other day, but we didn't do it in such a way that the converting way. And I felt like I couldn't teach you the converting way till we learned these properties today, so it just would have been a little overwhelming. So let's go ahead and try these problems from lesson 37 from last time, okay? Let's set this up. It says, how long will it take 7,000 to grow to 10,000 when it's compounded annually at this rate? They use the word compound, so I know I need to use one of the interest problems, right? And then they use the word annual, so I know n is, it's not continuous, so I don't use the e. I use the n one, right? Now, we want to know how long. So our unknown is up here in the exponent. It's not one of these now, right? Where do I put values in that formula? So here was our formula. I'm using a y, but we used a when we wrote it in your notes. Sorry, I should have just used an a. Here's the formula. What goes where? This left side stands for future amount, right? So what's our future? It's growing to what? 10,000. Good. Initial was 7,000. 1 plus, what do I write my rate as? 0.032, right? It's going to be compounded how many times in a year? It says annually. Once. Okay, and so I raise it to a 1, and then they want to know how long. Well, so now our variable is stuck up in the exponent. So when it's stuck up in the exponent, we will use logs to solve this, okay? Now, we'll start to isolate. So first you want to clean it up so that it's just an exponent equal to a number. So we really do want to pull this 7,000 away, because I can't distribute the 7,000, right? So we're going to pull the 7,000 away. This is 10 over 7. I'm going to leave it as 10 over 7. Let's clean up our base so we know what our growth constant, our growth ratio or constant is. What what do? I normally divide by 1 first. So I notice a couple people are having problems with their calculator. They're getting wrong answers. So make sure when you're doing this inside part, you divide first and then add that number to it. This one's nice because it's just divided by 1. So my constant is really easy to come up with, is that, right? And then my top, I normally would have a number here, 1 times t, but we luckily just have a t. This is where you guys get to use the knowledge you just learned. You guys can convert this to a log to solve. Now I had taught you to ln both sides, which I will still go back to that, but let's use the properties we just learned, okay? Now this is a bummer because your base is really ugly. My base, my log is gonna be a base what? Yeah, so it's not pretty, okay? But it's gonna be the log of 10 over 7 with that base will be equal to my t, and this is something I can do the change of base formula with. So it gets to go in as the change of base formula, and now we know those properties, so we can do it, okay? And I apologize for not being able to do this last time with you guys. Will someone put that in their calculator and tell me what you get? Close parentheses, if you're not getting the right answers, it could be that you aren't closing parentheses.
How many decimals do you want?
Let's go a couple, like 3, maybe 2 or 3.
11.323.
So 11 point, you said 333?
323.
323, awesome. So it's gonna take that many years. Okay, now let me talk to you about the way I did it the other day. We have been drilling into your minds the converting thing, but what you guys do to one side, you do to the other. There are these log properties that I don't know if you guys remember from last year, but on my earlier question, do you guys remember me logging both sides? You guys could have chosen to log with a base 1.03 and then log. You guys can also do the balanced equation way instead of the converting way. You guys could log with this base and log with this base. So I had ln to both sides. I had ln instead of 10 over 7, and then I had ln this 1.032. And this is, hey look,
Hello.
this is the tricky part. This is a property we didn't bring up yet, and we are going to hit this heavier in Math 1050. Do you guys remember from last year that when logs are involved, that this exponent can be brought down? Does anybody remember those properties, those expanding properties? If you remember those properties, that's why on your earlier example I did it this way. I am technically allowed to bring my t down, and it's now a times with the ln, and then this ln can be divided over. Well, what does that look very similar to that you guys just put in your calculator? The change of base formula. You guys had just put in log of 10 over 7 divided by log of 1.032. So there's 2 approaches. Convert to an exponent approach, or ln both sides so you can pull the exponent down and then divide. So 2 approaches to how you guys can solve for t. Alright, so those of you who have any t questions on lesson 37, I do apologize, and hope you guys can go back and finish those. Alright, you guys are good to